Good day, everyone. My name is Caibigan, and I'm here today with my group mates, Camonias and Tarog. And also, let me introduce our instructor, Professor Jonathan Taylar. Uh, so we're going to talk about the creation of stroke prediction machine learning. So first, let me call on Christine Tarog to discuss the data sets.
So for our stroke prediction using machine learning, we first need to import the necessary libraries needed for this study or for this machine learning, like uh, installing or importing the libraries for our graphs for the data analysis. And after importing the necessary libraries, we are now going to import or load the dataset, which is the healthcare dataset stroke data, that CSV, that we got from kaggle.com. So after the dataset has loaded, these are now the contents of the dataset. The columns are ID, gender, age, hypertension, heart disease, ever married, work type, residence type, average glucose level, BMI, smoking status, and stroke. So as you can see, some of the columns have a string value. So we are going to convert it into numerical value later on. So after loading the dataset, we are going to drop some columns that is not necessary for the machine learning or for the our stroke prediction, like the ID. And after that, we are just going to prepare our data for the data analysis, like showing the different possible graphs of the data. And can you show some of our graphs, like this one? So moving on, for this one, we are going to set unique values to the data. Like for our um, for the yes or no answers, we are going to set 0 and 1 numerical value for it. So to be able to convert our string types, we are going to use the one-hot encoding method, in which there is a process by which categorical variables are converted into a form that could be provided to ML algorithms or machine learning algorithms to do a better job in prediction. So this method will help us to convert string values into numerical type for for the machine to be able to read the data of our data set. So after converting the needed values or the string values, we are now going to move on to the classifiers that we use. So we first use the train test. So for the train test, this is the machine learning algorithms that are applicable for prediction-based algorithms, and applications are evaluated using the train test split. And we also use the data normalization, in which, in order to secure the data and increase the database's flexibility by removing redundancy and inconsistent reliance. These involve constructing tables and defining relationships between those tables in accordance with rules. We also use decision tree, that is a decision tree making diagram where the branches indicate options and the leaves reflect risk, columns, outcomes, or possibilities, and which is used in business or computer programming. We also used the KNN, or the K-neighbors classifier, in which this is the idea, or the idea is that the predetermined features establish a space in which known data are ordered. So the algorithm which will decide the class of the new data when it receives new data by comparing the classes of the k nearest data. Next classifier, Jane.
So the next algorithm will be logistic regression, that when a variable is categorical, the proper regression analysis to use is logistic regression or binary. The logistic regression is a predictive analysis just like all regression analysis to describe data and explain the relationship between one dependent binary variable and one or more independent nominal, ordinal, interval, or ratio level variables. We employ logistic regression. The next algorithm is random forest. Uh, on various samples, it constructs decision trees and uses their average for classification and majority vote for regression. And the XG boost, it combines the predictions of a number of a weaker, simpler models in an effort to properly anticipate a target or variable or a target variable. And the SVM or support vector machine. Using a kernel function, data can be input and then transformed into the format needed for processing, which means the kernel is employed because the window for manipulating the data in a support vector machine is provided by a set of mathematical operations. So, for training and test, um you need unknown data and no, I'm sorry. Uh the training and um score will be discussed by J. Camonias.
Okay, thank you, Miss Caibigan. Now first, if you run these codes, we got these results. For the Gaussian naive Bayes, we got trained score of trained model 70.95, test score of trained model 18.17, and a confusion matrix 145 to 1 and 823 to 38. And for the Bernoulli naive Bayes, the trained score of trained model 95.73, the test score of trained model 95.83, confusion matrix 965 is to 39, and 3 is to 0. We have the logistic regression, trained score of trained model 96.08, test score of trained model 96.13, confusion matrix 968 is to 39, and 0 to 0. Next, random forest classifier, trained score of trained model 100, test score of trained model 96.03, confusion matrix 967 to 39, and 1 is to 0. Support vector machine or the SVC, trained score of trained model 96.08, test score of trained model 96.13. 96 confusion matrix is 968 is to 39 and 0 to 0. Decision tree classifier, trained score of trained model 100, test score of trained model 92.85, confusion matrix 930 to 34, and 38 is to 5. The K neighbors classifiers, the trained score of trained model 96.13, test score of trained model 96.23, confusion matrix 968 to 38, and zeros to 1. And we have the gradient boosting classifier or GBC, the trained score of trained model 96.50, test score of trained model 96.03, confusion matrix 967 to 39, and 1 is to 0. Lastly, the stochastic gradient descent, trained score of trained model 96.08, test score of trained model 96.13, confusion matrix of 968 to 39, and 0 to 0. And the trained test score of models. So here's the bar graph of the total models or total classifiers. We have these algorithms. So accuracy of Gaussian and naive Bayes 18.17%. Accuracy of Bernoulli naive Bayes is 95.83%. Accuracy of logistic regression 96.13. Random forest classifier 96.03. And for support vector machine 96.13. Decision tree classifier 92.85. K-neighbors classifier 96.23. Gradient boosting classifier 96.03, stochastic gradient descent 96.13, lastly neutral nets 92.35. And the highest is the accuracy of K-neighbors classifier. We have 96.23%. And for the evaluation of models, so we evaluated these models according to their accuracies. Best algorithm is KNN with 96.03%. So we will make k-fold cross-validation and hyperparameter optimization for KNN algorithm. So here's the code for that. And after that, here's the result. Train score of train model 0.96, test score of train model 0.96, accuracy 96.23%. And have a confusion matrix 968 to 38 and 0 is to 1. Saving the best model prediction, save KNN model. And the k-fold cross-validation will enable us to see whether we are facing an overfitting problem and also to see the quality of our model. Thus, it will be enable us to test the performance of our model before encountering high error rates in the test data set that we have not seen yet. It is a method that is frequently used because it is easy to apply. Here it is, the cross-validation scores and the scores here. So accuracy mean 93.75%, the standard deviation of 88.39. And for the hyperparameter optimization, it is the process of finding the most suitable hyperparameter combination according to the success metric specified for a machine learning algorithm. So given that there are dozens of hyperparameters for a machine learning algorithm and dozens of values that these hyperparameters can take, it's clear how difficult it will be to try all combinations one by one and pick the best combination. For this reason, different methods have been developed for hyperparameter optimization. Grid search CV and the randomized search CV are among these methods. So here's the grid search CV. For the hyperparameters and their values, that are desired to be tested in the model. A separate model is established with all combinations and the most successful hyperparameter set is determined according to the specified metric. So here's the result, fitting 5 faults for each 384 candidates, totaling 1,920 fits. And here's the grid search view best score, 95. The best estimators, k-neighbors classifiers, metric, Euclidean, and neighbors is equal to 3. The params algorithm, auto, metric, Euclidean, and n neighbors 3 weights uniform. And the randomized search CV, a set of hyperparameters is randomly selected and tested by cross-validation and the model setup. So these steps continue until specified calculation time limit or the number of iteration is reached. For this is fitting 5 faults for each 200 candidates, totaling 1,000 fits. And for the best score, 95, best estimator K neighbors classifiers, and best params weight, uniform, and neighbors, 3 metric, Minkowski, algorithm, and auto. And for the best feature selection, so we have this total number of sample in the whole data set. We have 5,035. And for the total of number of sample in trained dataset, we have 4,028. And for validation dataset, we have only 503. And for the test dataset, we have 504. And the random forest classifier old shape is 5,035.19. And we have this new shape becomes 5,035, but only 3 in variable y. And next is we have this decision tree classifier. From 5,035 to 19, we have the new shape 5035 3. So just like in random forest classifier, I guess they're same all models. Ay, okay. So here, oh, in Bernoulli knife base, we have 5035 old to 19. We have the new shape of 5035 and 7. For logistic regression, the new shape is 5035 and 10 for the variable y. Lastly, for stochastic gradient descent, we have the new shape of 5035 and 7 for variable y. Now for the conclusion, in this notebook, we examine stroke prediction dataset. We analyze the dataset, then tested various ML algorithms for the one with best accuracy. We save it for using with GUI for providing prediction to the user for chances for stroke to him or her, based on the data provided by him or her using GUI. And thank you. Okay, for the final accuracy, so here's the result. For Gaussian knife base of 18.46%, Bernoulli knife base of 90.72%, logistic regression 91.86, random forest classifier 93.63, support vector machine 92.46, decision tree classifier 92.06, k-neighbors classifier 96.03, gradient boosting classifier 94.63, stochastic gradient descent 94.83, and lastly, we have the accuracy of neutral nets of 93.05. So all of these accuracy we're going to use in the app.py, which is to be discussed by Miss Caibigan.
So for the app.py or application.py, um, we imported the job library, the NumPy, the Flask to import Flask render templates and requests. So for uh, there are three defined variables, which is the index, the about, and the result. So for the index, it is the home page or the first page of the application. And the defined about is the result of the input data. So the defined result is where the get and post happen. So for um post and get uh variables, um the method attributes specifies how to send form data. The form data is sent to the page specified in the action attribute. The form data can be sent as URL variables with method get. So that's where the form data can be sent. And for method post, uh, it is where you send the form data. So for you can see uh, in the result, in the defined result, uh, there's so here is where the inputted data. Can you put it in the result? Defined result. So y- we use the scalar paths. So the models or the scalar.pkl uh, is used. And for modal path, we use the model.sav. So y prediction for y prediction at it is equals to dt dot predict or the x. And then after that, we will print the result as y underscore predict. Then if y predict is equals to 0, it will show no stroke or um there is no possible way that the what you call this, the user or the inputted data has no stroke. And the else tag or else algorithm, we use the return render template to stroke that HTML or the other page or the defined about. So if the y predict is equals to 1, then it will go to the other page, which the results will be stroke, or the person is or has a stroke. Then if name is equals to main, then the app will run. So that's let's show the actual application, and will be presented by J Camonias. So first we need to change the directory to downloads, next to stroke prediction, and the other file name. So here's the directory. Then um we're going to activate an environment or create by inputting Python 3. Yeah. So we will copy the address or IP address in order to run the app or the application.
Okay, thank you, Miss Caibigan. Now, for the output of our project, so we have this homepage. So, consists of quiz prediction by BET-CPET 3D STEM or Group 5, and input your data. So, here is you need to input your data. Let me ask Miss Tarog to give me the details of some patients that we use in our dataset.
So first, let us input the gender. Let's try to input male. And then the age is 67. Hypertension, yes. Heart disease, no. Married, yes. Then employment is private. Then residence type is urban. Then the average glucose level is 228.69. And for the BMI is, let's just say 37. For the smoking status, formerly smoked. So with our given data, it shows that the subject has no data risk. Let's try to input with data or with stroke risk. I'm sorry. So let's try again with the female and the age of 80. Hypertension, no. Heart disease, yes. Marital status, yes. Employment, never worked. And the residence type is urban. The average glucose level is 80, and the BMI is 20. I mean 120, sorry.
What?
120. And never smoke. Oh, I mean smoke regularly. Sorry.
The value must be less
So
than
let's try to change it into 87.
87.
There you go. Now it shows that our input data has a stroke risk. So these are this will be the notifications that we will get if we have a stroke risk. And a while ago, it shows that it has a no stroke risk. So this is our stroke risk or stroke prediction machine learning. Jane?
So that will be all for our machine learning. And thank you for um, listening and watching our presentation.